Don't forget to subscribe and drop a like. That way you won't miss any new uploads. In the spring of 1946, the U.S. Army Ordnance Department began systematic evaluation of captured German armored vehicles at Aberdeen Proving Ground, Maryland. Among them was one of the most technically significant machines of the war, the Panzer Kampfwagen V Panther. The vehicle arrived in late March 1946 after months of shipping and decontamination in Europe. The tank had been captured intact near the city of Trier in March 1945 by elements of the 11th Armored Division. It was an Ausführung G model, chassis number 120790, produced by Maschinenfabrik Niedersachsen-Hanover, M&H, in December 1944. Despite minor battle damage and missing side skirts, the vehicle was mechanically complete, its Maybach HL230P30 engine still functional after field servicing. At the port of Cherbourg, Army Ordnance technicians drained and cleaned the fuel system, replaced the oil and installed temporary transport tracks. The Panther was shipped aboard the Liberty ship SS Fort Mercer and reached New York Harbor on March 8, 1946. From there, it was moved by flat car to Aberdeen Proving Ground APG, under consignment No. X6112. Officially it was listed as German, Tank PZ.KWV Panther, WT 45 tons. The receiving paperwork recorded its overall condition as good, runnable, with turret traverse operable by hand and electric motor intact. Paint remained in the late war ambush camouflage pattern, Dunkelgelb base with Rotbraun and olive grun spots. The test series at Aberdeen followed the Army's standard captured material evaluation protocol. The purpose was to study armor metallurgy, internal layout, mobility performance and ballistic resistance under U.S. ammunition. The staff assigned the serial AFV No. T88. Comparative tests were planned alongside an M26 Pershing and AT-26 E3 pilot vehicle. The Ordnance Board's interest lay in three areas: armor hardness and sloping, reliability of the final drives, and ballistic protection against the U.S. 90mm M3 gun. On April 4, 1946, the Panther was rolled onto the test course at the Western Field area. The crew consisted of 2 ordnance engineers and 1 enlisted driver, T/4 Harold E. Miller, trained in German controls. The tank weighed 44.8 metric tons combat loaded. Its HL230P30 12-cylinder gasoline engine displaced 23.1 liters and produced 700 metric horsepower at 3,000 revolutions per minute. A 7-speed AK7 to 200 transmission and double differential steering gear transferred power to the front drive sprockets. Suspension was the characteristic interleaved torsion bar system with 8 double bogie road wheels per side. During preliminary checks, the team measured idle oil pressure, 5 kilograms per square centimeter, coolant temperature rise from 22 degrees Celsius to 85 degrees Celsius in 12 minutes, and fuel consumption at idle, 8 liters/hour. Compression readings varied between 95 and 105 psi, indicating moderate wear but serviceability. The engine started reliably using the Bosch electrical system and twin magnetos. Noise level at driver's position reached 108 dBA, typical for late-war German tanks. Road tests began on the 3.2-mile concrete loop. Average speed over the circuit was 30 km per hour, with a maximum of 46 km per hour recorded on the straight. Steering response was described as progressive and accurate at high speed, heavy at low speed. Fuel consumption averaged 2.8 liters per kilometer, approximately 0.35 miles per gallon, slightly better than data from British post-war trials at Chertsey. The testers noted strong acceleration for its weight but recurrent overheating above 2,800 revolutions per minute. The final drives, a known weakness in combat, were inspected after 21 miles. The left planetary housing showed metal dust and minor pitting, confirming prior German field reports. After mobility trials, attention turned to armor evaluation. Chemical analysis of a 90 by 90 mm sample cut from the glassy plate, 80 mm thickness at 55 degrees slope, revealed carbon 0.42%, manganese 0.83%, nickel 1.8%, molybdenum 0.31%, and chromium 1.1%. Brunel hardness averaged 260 HB. The side armor, 40 mm at 40 degrees, registered 310 HB. The U.S. metallurgists remarked on uniform heat treatment and fine grain size, though some microcracking was observed near weld zones due to late-war material shortages and higher sulfur content. Welds were hand-laid with minimal porosity. Ballistic tests were carried out between May 15 and June 2, 1946, on the outdoor range at APG. Sections of the Panther's hull were fired upon using standard U.S. test ordnance. The 90mm M82 APCT projectile from the M3 gun, and the 76mm M62 APC round from the M1A1 gun. Results were as follows. At 1,000 yards, 76mm M62 failed to penetrate the 80mm glassy 55 degrees, confirming German reports that the Panther's frontal armor resisted all Allied medium tank guns. At 600 yards, 90mm M82 penetrated cleanly, producing a 100mm diameter hole with minor spalling. The lower glassy, 60mm at 55 degrees, was vulnerable at 900 yards to the same projectile. Side armor, 40mm vertical, was perforated by 57mm M70 AP at 1,200 yards. Observations recorded excellent ballistic shaping and efficient use of slope to reduce effective impact angle. The Ordnance Summary noted that frontal immunity zone against 76mm APC extended to 200 yards, confirming the qualitative edge of the Panther's armor design over most Allied mediums of 1944-45. On June 10, the turret traverse mechanism was tested under power. The electric drive 24V Bosch motor 1.5 kilowatts rotated the turret 360 degrees in 18 seconds, slower than the M26's hydraulic system but smoother. Manual traverse required 150 pounds effort on the crank, acceptable for field conditions. The hydraulic gun stabilization mechanism, long rumored in Allied intelligence, was absent. Elevation was manual through worm gearing. The main armament, the 7.5 cm KWK-42L/70, serial number 89732, was bore-sighted and fired with captured ammunition. Muzzle velocity averaged 3,070 feet per second using PZGR. 3940 seconds, APCBC, rounds. Dispersion at 1000 m was 0.22 mil, giving 22 cm mean radius at that distance, superior to US 75mm M3. Recoil measured 370 mm, consistent with German specifications. The U.S. testers fired 10 rounds at an armor steel plate. Penetration at 30 degrees impact angle was 149 mm at 500 m. The Aberdeen report emphasized that the KWK-42 remains among the most efficient high-velocity tank guns yet tested, exceeding 17-pounder in ballistic energy at equal ranges. Crew ergonomics were evaluated by Major G. H. Sparks' team. The interior was judged compact but logically arranged. The commander's cupola offered 360 degrees vision through 7 periscopes of 90 degrees overlap, rated excellent visibility compared to U.S. designs. However, ammunition stowage, 79 rounds, was deemed hazardous. Shells around the hull sides lacked flameproof containers. The escape hatch under the gunner's seat was small and obstructed by traverse mechanism, a weakness also noted in British reports. By late June the Panther had completed 240 miles, 386 kilometers, of cross-country driving. Average mechanical availability stood at 82%. Failures included cracked left track link, seized fan bearing and minor fuel leak. Test data recorded average ground pressure 0.88 kilograms per square centimeter, comparable to the M26's 0.90. Cross-country speed on moderate terrain averaged 16 kilometers per hour. Trench crossing 2.45 m, vertical obstacle 0.85 m. For deep mud traction the wide 660 mm tracks performed effectively, though clogging between interleaved wheels proved chronic in clay soil. Crew reported extreme difficulty removing inner road wheels for maintenance. At the metallurgical laboratory, ballistic cut sections were compared to captured Tiger I and Tiger II plates. The Panther's alloy balance showed better uniformity than late production Tiger II samples, which suffered brittle failure due to low molybdenum content. The report, Ordnance Department File No. TS30-603, concluded, armor composition of PZKW-VG represents the optimum balance achieved by German industry under 1944 conditions. Parallel with Aberdeen testing, another Panther, an OSF, captured by the British 21st Army Group near Beckham, was tested at Chertsey's Fighting Vehicle Proving Establishment, FVP. Data exchange between British and U.S. experts occurred via liaison in July 1946. The U.S. found general agreement, excellent gun and frontal protection, poor reliability of final drives and running gear. In August the U.S. Army initiated firing tests using high explosive and heat ammunition against the Panther to simulate future anti-tank weapons. The 90mm Heat M71 round penetrated the glacis at 90 degrees within 900 yards, producing a 70mm entry jet and catastrophic interior spall. Photographs from this test. APG Ordnance Report Fought. Number 184-46. Show burned interior paint and deformation of the commander's cupola. These images later appeared in Technical Manual TM9-1985 German, issued 1947. The ordnance engineers were struck by the compactness of the German power pack. The HL-230 engine's aluminum components, oil cooler housings, intake manifolds, demonstrated precision casting uncommon in Allied designs. The fuel system used twin 290-liter tanks feeding a Bosch-type fuel pump. Octane requirement was 74 minimum. Test runs showed knocking with US 80-octane aviation gasoline unless mixture enriched to 10.5. 1. The cooling system comprised twin radiators with 2 times 700mm fans belt-driven at 1.3 times engine RPM. Under ambient 30 degrees Celsius, coolant stabilized at 95 degrees Celsius. Lubrication consumption averaged 1.2 liters/hour, twice that of the M26. By autumn 1946, cumulative mileage reached 327 miles. The final drives failed catastrophically during a September run when the right reduction gear seized. Disassembly revealed fractured sungear teeth from fatigue cracks propagated through case-hardened steel, precisely the defect German Panzer maintenance logs had recorded since 1944. The U.S. Army engineers concluded that final drive assembly remains underdimensioned for engine torque, probable design compromise due to weight limitation. The Panther's radio equipment, FUG-5 transceiver, 27.2 to 33.3 MHz, was tested but not operated on U.S. frequencies. Range with 2M rod antenna measured 3.2 miles voice, 6.8 miles CW. The intercom system functioned but lacked noise suppression, making conversation difficult above 2,000 revolutions per minute. Electrical wiring employed fabric insulation, some already degraded. Voltage fluctuations between 23 to 26 V caused turret motor surging. The official APG report, finalized December 20, 1946, filled 142 pages. Its conclusion summarized. Firepower, outstanding. The 7.5 cm KWK-42L/70 combines high muzzle velocity with good ammunition design. Equivalent or superior to US 90mm M3 in armor penetration at 1,000 yards. Protection, superior frontal defense due to slope, sides and rear inadequate. Armor quality excellent, though welds occasionally brittle. Mobility, high tactical speed and good cross-country mobility. Mechanical reliability below U.S. standards due to overstressed transmission and complex suspension. Crew efficiency, good vision and optics, poor comfort, high heat and complicated maintenance. Manufacturing quality, excellent machining and finishing despite wartime shortages. The report's closing remarks stated, German Panther tank represents the most advanced compromise of firepower, protection and mobility produced during hostilities 1939-45. However, maintenance burden and component fragility reduce its field value. In January 1947, the surviving hull remained at Aberdeen for static display. The transmission and engine were removed for metallurgical storage. One of the KWK-42 guns was shipped to Watertown Arsenal for further ballistic analysis. The chassis, rusting slowly in Maryland humidity, would decades later be preserved and restored for the U.S. Army Ordnance Museum. But in 1946, to those who tested it, the Panther was neither relic nor curiosity. It was an opponent studied with respect, a symbol of the technological race that had only just ended. Its data influenced post-war American design studies such as the T-42 medium tank and early models of the M-46 Patton, in which slope, armor hardness and high-velocity gun lessons drawn from German engineering were quietly embedded. By the beginning of 1947, the Aberdeen Ordnance Staff extended the Panther evaluation program to include comparative firing and endurance trials with contemporary U.S. vehicles. The focus was no longer merely descriptive but analytical, how lessons from the German tank could shape post-war American designs. The Panther chassis, designated Test Vehicle T-88, served as a control sample in what was officially titled Comparative Evaluation of Medium Tanks, German and U.S., 1946-47. The M26 Pershing T26E3 pilot model, and a modified M4A3E8 equipped with HVSS suspension formed the U.S. reference group. The winter of 1946-47 was one of the coldest on record in Maryland, which allowed engineers to study cold start reliability and lubricant behavior at sub-freezing temperatures. The Maybach HL230 engine required extended preheating, up to 45 minutes using electric block heaters, whereas the Ford GAF V8 of the M4A3E8 started reliably after 5 minutes. The Panther's oil viscosity demanded dilution with gasoline during cold start, as the original German manual prescribed. Even with all cylinders firing, the mechanical drag of the complex transmission made first movement sluggish. Notes from test driver Sergeant Miller read, "Clutch effort extreme when cold, gearbox box into second, steering stiff until warm-up." These operational traits confirmed combat reports from both Allied and German sources about difficulties during winter campaigns. Once warmed, however, the Panther demonstrated remarkable mobility for a 45-ton vehicle. On frozen ground, its wide tracks distributed weight effectively, enabling it to outperform the M26 in traction tests. Pulling trials using a dynamometer car measured tractive effort of 15,200 pounds at 8.5 miles per hour, nearly equal to the heavier Pershing's 15,800 pounds. The suspension, though complicated, provided exceptional ride smoothness. Oscillograph data from accelerometers placed on the commander's seat recorded peak vertical acceleration of only 0.52 g over a 0.5 meter bump, compared to 0.76 g in the M26. American testers admitted the German torsion bar system with interleaved wheels produced a superior ride, though they condemned its maintenance impracticality. Attention then turned to gunnery comparisons. On February 13, 1947, Aberdeen's Ballistic Research Laboratory, BRL, conducted a direct firing trial between the Panther's 7.5 cm KWK 42L/70 and the US 90mm M3 gun mounted on the Pershing. Both weapons were fired from prepared mounts against standardized armor plates of homogeneous steel, US specification MO12560. The results were instructive. The German gun, despite its smaller caliber, delivered nearly identical penetration due to higher muzzle velocity and superior projectile design. The APC-BCG PZJR 39-40 round, weighing 6.8 kilograms, achieved 138 mm penetration at 30 degrees at 1,000 meters, while the American 90mm M82 APCT, 10.9 kilograms projectile, 853 meters per second, achieved 150 mm under the same conditions. The marginal difference highlighted the German emphasis on velocity over shell weight. Ballisticians remarked that, at typical combat ranges below 1,200 m, the Panther's weapon equals or surpasses our 90mm in flatplate performance. Optical evaluation followed. The German Turmziel-Fernrohr 12A, TZF 12A, telescopic sight, with 2.5 times and 5 times magnification, impressed the testers. Resolution measured 6.2 arc-seconds, almost double that of the M71C telescopic sight used on the Pershing. The reticle, calibrated for 1,000 to 3,000 meters in 100-meter increments, was precise but required manual range estimation. No coincidence rangefinder existed. In bright light, the crosshair etched in the optical glass remained visible without internal illumination, a simplicity American evaluators appreciated. BRL concluded, German optics exhibit exceptional workmanship and image clarity, with coatings equal to contemporary Zeiss civilian lenses. This statement later influenced the U.S. post-war contracts with Bosch and Lohm and Kodak for multi-coated tank periscopes. The armor metallurgy section expanded in early 1947. Samples from the Panther's hull and turret were compared with those from a captured Tiger II and a U.S. T-29 heavy tank prototype. Spectrographic and micrographic studies confirmed that by late 1944 German steelmakers had succeeded in producing relatively homogeneous armor with reduced nickel content compensated by molybdenum additions. Hardness varied between 255 to 300 Brinell. Impact tests at -40 degrees Celsius revealed only slight embrittlement, whereas US 240 BHN plates fractured more easily under identical conditions. The Metallurgy Division noted, the German technique of through hardening followed by low-temperature tempering yields superior impact resistance for thicknesses under 90 mm. Nevertheless, welds displayed sulfur inclusions and occasional porosity, likely due to oxygen scarcity in late war production. The Army also evaluated German design philosophy as expressed in the Panther's sloped armor geometry. Using a specially constructed mock-up, the ballistics branch measured the effective thickness of the 55 degrees glacis. The formula, actual thickness divided by cos angle, Gave 80 divided by cos 55 degrees equals 139 mm equivalent line of sight. Experiments with 76 mm and 90 mm projectiles confirmed that ricochet probability exceeded 60% at impact angles above 55 degrees, explaining Allied field observations that most hits on the glacis simply deflected. These quantitative findings directly informed later U.S. armor configurations. The M46 and M47 glacis plates adopted 60 degrees slopes with 100 mm base thickness, following Panther-derived calculations. By mid-1947, the Panther test vehicle's mechanical condition had deteriorated. Repeated running caused failure of both outer final drive bearings. Spare parts were non-existent, forcing machinists to fabricate replacements from U.S. steel stock based on German drawings. Maintenance logs record over 420 man-hours spent keeping the tank operational. Engine compression had dropped to 90 psi average, oil consumption exceeded 2 liters/hour. Fuel remained 80-octane aviation gasoline. Consumption stabilized at 0.33 miles per gallon. Despite wear, the vehicle continued to run. Engineers intentionally pushed it to failure during an endurance test in August. After 41 miles, the right final drive seized completely, immobilizing the tank. The resulting teardown produced valuable metallurgical data on fatigue and case-hardened gears. Under microscope, fine radial cracks indicated stress concentrations from gear tooth profile under load, exactly as German field reports described at the time of the Battle of Kursk. Parallel comparative studies were performed at Fort Knox, where an identical model Panther, OSF, provided by the British was temporarily loaned. The Armored Board compared maintenance times and crew procedures. The data, summarized in Armored Board Project 269, September 1947, found that complete track change on the Panther required 6.5 man-hours versus 1.8 on M26. Engine removal required 25 hours versus 12 on M26. The complexity of interleaved wheels increased mud accumulation and freezing hazards. Maintenance officers concluded that the German emphasis on technical refinement reduced practical field maintainability. In October 1947, ordnance engineers ran the final controlled firing tests on the damaged Panther hull. The vehicle was anchored on the range, stripped of internal equipment, and used as target for a sequence of experimental high-velocity projectiles. The main objective was to test new U.S. armor-piercing discarding SABO, APDS, rounds under development. The 76mm VAP-TM-93 round at 1,030 meters per second cleanly penetrated the upper glacis at 600 yards, confirming that by late 1945 U.S. tungsten cord ammunition could defeat Panther frontal armor. Photographs from the test show sharp-edged entry holes with minimal spall, a characteristic of dense core penetrators. These results closed the circle. Weapons designed in response to the Panther were now finally capable of destroying it. Data from these trials influenced two major post-war U.S. development programs: the T-42 medium tank, which evolved into the M47, and the T-54 experimental gun series. The T-42's armor slope and overall height reduction were directly inspired by Panther measurements. Likewise, the 90mm T-15E2 gun used in the T-54 project sought to replicate the high velocity and accuracy of the German 7.5 cm KWK-42. In internal correspondence dated November 5, 1947, Colonel William S. Wainwright, chief of the AFV section at Aberdeen, wrote, "While maintenance of captured German equipment has proven costly, the educational value of the Panther program cannot be overstated. The principles of sloped armor, efficient ammunition ballistics, and balanced design inform all current medium tank projects." By December 1947, the Panther test vehicle was officially retired. The HL-230 engine was removed and sent to the engineering division for teardown. Detailed measurements followed: bore 130 mm, stroke 145 mm, displacement 23,095 cubic centimeters, compression ratio 6.8 to 1, maximum torque 1,850 Nm at 2,200 revolutions per minute. The crankshaft, machined from nitride steel, exhibited surface hardness of 420 HV. Main bearing were measured up to 0.15 mm. The engineers noted high machining quality of the crankshaft journals and precise counterweight balancing. Pistons were aluminum alloy with 3 compression rings. Ring wear remained within acceptable limits despite long use. Cooling jackets showed localized corrosion, likely from wartime coolant shortages and substitution of untreated water. Testing of transmission AK-7-200 revealed why mechanical failures were frequent. The planetary reduction gear, using straight-cut gears, produced high contact stress. U.S. analysis suggested the design, while compact, lacked sufficient tooth width. Stress analysis estimated 130,000 psi surface stress at 600 horsepower input, exceeding safe limits for the used materials. Recommendations for future U.S. transmissions included helical gears and improved heat treatment, adopted later in the CD850 series used in the M46 and M47. In March 1948, the Panther's remaining hull sections served for explosive tests. The demolitions branch investigated shape charge behavior on sloped armor. A U.S. 105 mm heat shell, impact angle 55 degrees, created a jet crater 120 mm deep but failed to perforate completely. At 90 degrees, penetration reached 160 mm. The conclusion stated that sloped armor remains effective against cumulative jet attack by increasing path length. This research contributed to understanding that later appeared in classified reports used for designing heat-resistant skirts on the M48 pattern. The final consolidated report, Ordnance Department Technical Memorandum No. 3395, captured enemy equipment evaluation, Panther tank, dated July 1948, summarized the two-year investigation. Its key findings read: ballistic efficiency. The Panther's frontal armor, sloped at 55 degrees, provided an equivalent vertical resistance of 138 mm. No U.S. 76 mm weapon could defeat it except with special ammunition. Firepower. The 7.5 cm KWK-42L/70 gun combined high velocity, approximate 1,125 meters per second with APCR, and excellent accuracy, capable of defeating 120 mm homogeneous armor at 1000 m at 30 degrees. Mobility. Maximum sustained road speed 46 km per hour, cross-country 20 km per hour. Fuel consumption extremely high, approximate 250 liters/100 km. Reliability. Below Allied standards. Mean distance between mechanical failures 150 km. Primary weak points: final drives, bearings, cooling fans. Crew layout. Ergonomic design with superior optics and observation. Inadequate ventilation, high noise levels. Design philosophy. Advanced integration of sloped armor and long-range firepower. Overcomplicated suspension and drive system. Production unsuited to mass warfare. The closing paragraph of the memorandum stated: the Panther tank represents a high point in German wartime engineering. Its design compromises, between the protection of a heavy tank and the mobility of a medium, exerted lasting influence upon post-war armored vehicle design. The United States has incorporated several of its lessons in the T-42 and T-48 series. By 1948, the surviving parts of the Panther were distributed among several U.S. research facilities. The hull remained at Aberdeen, the turret was sent to Fort Knox, and the gun tube to Watertown Arsenal. The Ordnance Museum displayed the complete hull in 1949 under the sign German Panther tank, tested 1946-47. The steel surfaces were heavily scarred from ballistic impacts, penetrations labeled with chalk markings indicating projectile type, caliber, and velocity. Visitors in later decades would see it as a relic, but the scars told a precise technical story: each hole, each mark, a measurement in the evolution of tank design. Through these exhaustive studies, American engineers learned more than how to defeat an enemy tank. They absorbed a philosophy of engineering. The Panther had shown how careful attention to armor slope, gun performance, and optical precision could compensate for material shortages or smaller caliber. In its failures, they also saw the limits of overcomplexity and insufficient industrial robustness. The data harvested from its destroyed hulls would echo in every major Western tank developed during the early Cold War. When the Aberdeen trials concluded in 1948, interest in the Panther did not vanish. Across Europe, other Allied nations had undertaken similar evaluations, each for its own purpose. Together, these tests formed the most comprehensive technical investigation of a single enemy vehicle in modern history. Between 1945 and 1950, the Panther was examined by the United States, the United Kingdom, France, and the Soviet Union. Their reports, different in tone but convergent in conclusions, established its place in armored development. In Britain, the first systematic testing began earlier, in 1945, at the Fighting Vehicle Proving Establishment, FVP, in Chertsey, Surrey. The British obtained 2 Panthers, 1 OSF. a captured near Cannes, and another OSV G recovered from a scrapyard near Antwerp. Both were operational. Their primary aim was to compare the Panther to the Cromwell and the then new Comet and Centurion Mk.I tanks. The report AT number 176, German PZ.KW, v Panther, General Examination, June 1946, recorded the first formal British impressions. It described the Panther as a masterly example of efficient ballistic shaping, but mechanically over-elaborate. Test mileage at Chertsey reached 475 miles before the left final drive failed, the same weakness noted in U.S. tests. British engineers observed that the tank could maintain 25 miles per hour, 40 kilometers per hour, cross-country, outperforming the Cromwell in mobility despite greater weight. However, repair times were judged excessive. Track removal required lifting equipment, and interleaved wheels clogged in wet clay typical of English terrain. British armor analysts also noted the efficiency of the gun system. Using 7.5 cm PZ 39-40 seconds ammunition, the Panther penetrated a 4.7-inch, 120 mm, British homogeneous plate at 1,000 yards, an impressive figure that surpassed the 17-pounders APC at the same range. Yet the rate of fire, only 6 to 7 rounds per minute, was slower than Allied standards. British crews found internal stowage awkward and ammunition retrieval slow. The FVP summary recommended the adoption of a higher velocity gun on the upcoming Centurion to ensure superiority. That recommendation directly influenced the selection of the 84mm 20-pounder gun fitted to the Centurion Mk.3 in 1948. France conducted the most extensive post-war operational testing. The French army inherited approximately 50 Panthers left behind by German forces in 1945, most of them in usable condition. These tanks formed the 503e Regiment de Chars de Combat, 503e RCC, based at Montmolon-le-Grand. Between 1946 and 1947, they served as interim equipment for training and maneuvers. French engineers of the Service Technique de Matériels Blinds carried out a detailed evaluation published in 1947 as Rapport sur le char allemand PZ.KW, v Panther, Essai de Service. French data confirmed much of what the Americans and British had found. The average fuel consumption measured 750 liters per 100 kilometers. Engine overhaul intervals were short, approximately 500 kilometers before major work. Nonetheless, the Panther was appreciated for its accuracy and range. During gunnery trials at SWIPS, the 7.5 cm KWK-42 achieved consistent hits on a 2x2 meter target at 1,800 meters. French crews valued its optics and the powerful gun, calling it précis comme un canon de forteresse. But maintenance proved impossible in peacetime conditions. Spare parts were unobtainable, and every mechanical failure demanded cannibalization of another tank. By 1948, only 8 Panthers remained serviceable. By 1950, none were operational. The French reports emphasized 3 lessons that shaped post-war doctrine: sloped armor geometry, low silhouette, and high-velocity guns. When France developed the AMX-13 light tank in the early 1950s, engineers cited the Panther's ballistic shaping as inspiration for the sharply inclined hull front and compact turret ring design. Archival design drawings from Atelier de Construction d'Issy-les Moulineaux, AMX. In 1951 bear annotations comparing slope angles directly to the Panther's 55 degrees glacis. While the Western Allies studied the Panther as a technical specimen, the Soviet Union had captured and tested several examples earlier, between 1943 and 1945. The most complete Soviet study was conducted at the Kubinka Proving Ground near Moscow. The first Panther, an OSV captured near Kursk in 1943, arrived heavily damaged but sufficient for initial examination. The Soviet report number 2884, dated November 1943, already identified the tank's powerful long-barreled gun capable of penetrating any Soviet medium tank at all practical ranges. The armor was judged effective but the engine unreliable. Soviet metallurgists noted the high hardness of the front plate, 260 to 280 HB, and confirmed that its slope rendered it virtually immune to 76.2 mm AP at all distances. However, mechanical endurance was rated poor. Field tests recorded an average of 150 km before breakdown, matching German frontline experience. Further Soviet testing in 1944-45 compared the Panther to the IS-2 heavy tank. The IS-2's 122 mm D25T gun, firing BR-471B AP rounds, penetrated the Panther's glacis only at distances under 600 m and angles less than 20 degrees, confirming formidable frontal resistance. In contrast, the Panther's 75 mm gun penetrated the IS-2's frontal armor at 1000 m under ideal conditions. Soviet engineers thus concluded that, in direct duel at medium range, advantage rests with Panther if first to fire. But the Panther's complexity and poor reliability led the Soviets to dismiss it as unsuitable for their mass production philosophy. The T-44 and later T-54 adopted the Panther's low profile and sloped armor but simplified all mechanical systems. By 1948, the technical exchange among allies was formalized under the newly forming NATO Standing Group on Armaments. Declassified memoranda show that data from the U.S. Aberdeen and British Chertsey tests were shared with Canadian, Belgian, and Dutch ordnance departments. The purpose was to establish a unified baseline for future tank designs in the Western Alliance. The Panther's balance of firepower and protection was taken as a reference point, an informal standard for the medium tank class. At Fort Knox, the Armor Board integrated these findings into the Tactical and Technical Trends Bulletin of 1949. It stated, "The German Panther, though operationally unreliable, embodies the essential balance of mobility, armor and firepower which defines the future pattern of main battle tanks." This was one of the first uses of the expression main battle tank, MBT, in an American document, directly tied to analysis of the Panther's characteristics. The MBT concept would replace the wartime division between medium and heavy categories, merging them into a single type capable of all battlefield roles. From a purely quantitative standpoint, the cumulative Allied tests established an accurate technical profile of the Panther. Combat weight, 44.8 metric tons. Crew, 5. Length, 8.86 m with gun forward. Width, 3.27 m. Height, 2.99 meters. Engine, Maybach HL 230P30 12-cylinder gasoline, 700 horsepower at 3,000 revolutions per minute. Transmission, AK 7 to 200, 7 forward, 1 reverse. Armor, glacis 80 mm at 55 degrees, lower front 60 mm at 55 degrees, sides 40 mm, rear 40 mm, turret front 100 mm at 12 degrees. Main armament, 7.5 cm KWK 42L/70, 79 rounds. Secondary armament, 2 times MG34, 5,100 rounds. Speed, road 46 km per hour. Operational range, 200 km road. These data points appear consistently across American, British, and French documents. They provided a factual benchmark for designers and historians alike. After 1949, with the emergence of the Cold War, interest in captured German equipment declined. The U.S. Army Ordnance Museum retained its Panther as a static exhibit. Britain scrapped its test vehicles except one preserved at Bovington. France melted most of its Panthers during the reorganization of armored forces in 1950. The Soviet examples at Kubinka were stored for instructional purposes until the 1960s, one surviving today in the museum's main hall. Yet the technical influence endured. The Panther's combination of sloped armor and a powerful long gun directly inspired the early Cold War tank generation, the Soviet T-54, the American M46 and M47, the British Centurion Mk3 and the French AMX-13 and later AMX-30. Every one of these vehicles carried some trace of the lessons learned from captured Panthers, either in armor geometry, ballistic design, or internal layout. The pattern of the modern main battle tank can be traced back through these lines of descent. Archival correspondence from Watertown Arsenal in 1950 mentions the continued use of Panther armor sections for ballistic calibration. A series of US 90mm T-33 HVAP tests used leftover glacis plates as standard reference targets because of their known slope and uniform hardness. Even when the vehicle itself was gone, its steel still served as a technical constant. The legacy extended into the academic and industrial spheres as well. American metallurgical studies based on Panther samples contributed to the development of the AISI 4340 armor steel family, standardized in the late 1940s. British optical engineers adopted elements of the German Zeiss sighting systems for the Centurion's No. 30 sight. French technicians studying captured infrared devices from Panther night fighting variants, with FG 1250 systems, influenced early night vision experiments at Sagem in the 1950s. All these derivative advances stemmed from the thorough, methodical examination of a single captured enemy machine. In that sense, the Panther's post-war life, was longer and more influential than its short battlefield career. By 1950, the last formal reference to the Panther in U.S. Army documents appeared in Ordnance Technical Report No. 5979, Comparative Study of Tank Armor and Gun Effectiveness. It summarized 5 years of Allied testing with a brief statement. The German PZ.KW Panther, while operationally obsolete, remains the defining representative of the World War II medium tank in its mature form. Its data are to be retained for baseline comparison. In the storage yards at Aberdeen, the Panther hull stood outdoors, streaked with rust, its camouflage faded under Maryland rain. Bullet impacts, labeled in white stencil, still marked where American gunners had fired. 90 mm APC 1,000 yards, 76 mm HVP 800 yards. The engine compartment lay open, the Maybach removed. The vehicle no longer ran, it existed only as evidence, steel testimony to the technological struggle of 1939 to 45. Visitors to the proving ground saw it not as a trophy but as a study in design. Precise, formidable, flawed. The story of the Panther's testing closed quietly. The documents went into the archives. The engineers moved on to new projects. Patent tanks, self-propelled guns, and the beginnings of the Korean War. Yet the lessons remained inscribed in the institutional memory of Western armored development. The importance of balance between protection and mobility, of simplicity over refinement, and of engineering grounded in production reality. When later generations of tank designers in the 1950s and 1960s drew the first lines of the M60, the Leopard 1, or the AMX-30, they did so knowing the results of those 1946-48 tests. The Panther had taught both what to emulate and what to avoid. Thus, by 1950 the evaluation of the captured Panther had come full circle, from enemy weapon to object of study, from battlefield adversary to teacher. The U.S. Army's careful documentation preserved every measurement: armor angles, gear tolerances, penetration graphs, fuel curves. No myth, only data. In those precise numbers lay the final verdict. The Panther was neither invincible nor a failure, but a machine that pushed the limits of its time. And in the quiet storage grounds of Aberdeen, surrounded by the silence of other captured relics, the rusting German tank remained, a monument not to victory or defeat, but to the relentless pursuit of understanding through engineering.